Hello everyone, welcome to day 7 of solving Advent of Code. Today was a fun day. It's always fun when you read the problem statement, you feel the urge to solve it in a certain way, but you know it's not going to work, and then you have to figure out how to do it properly. That's what happened to me today. So we're going to take a look at that in a second. As per usual, just the usual disclaimer, I have solved the problem already. You can see in the backgrounds I have 2 stars for the 7 already, so this is a solution that I have prepared for the stream. And if at any point you have any questions, any comments, any remarks, feel free to put them in the chat. Hello Ivan, how are you doing today? Alright everyone, so without further ado, let's get cracking. How do I do this? This is what I want. Okay. So the problem statement gives you an input like this. Can I zoom in a bit more? So you have an S that marks your starting spot, and you have a beam that is going to travel down. And each time you find one of these characters, I think this is the name, carrots. Okay. So whenever you find one of these carrots, the beam splits. And this is shown in the diagram below. So the beam starts by going down, and as soon as it hits this carrot, it's going to split into a left and right beams. So now you have 2 beams going down. And they keep going down, and then they split again. And for part 1, what you have to do is, given your input, which is a bit bigger than this, you have to figure out how many times in total any beam splits. So in other words, you want to count how many times your beams hit these carrots. Now when I saw this, my first, and especially because of the demonstration with their diagram, my impulse was to simulate the full process of the beams going down and hitting the carrots and splitting. But since I'm not printing anything, since I won't be visualizing anything, there is a slightly better way of doing this. What I'll do is, for each row, I'm going to keep track of 2 things and 2 things only. The positions of my beams and the positions of the splitters. So then, when I have the beams of one row and the splitters of the row that's under it, I know exactly which beams will split and which beams will not split. The beams that will split are the ones that have a carrot in the same position in the next row, and the beams that don't split are the ones that don't. So I just need to keep track of those 2 things instead of simulating the full pattern. So what does this look like in code? Let's create a file. Alright, so to parse my input, I'm going to open my file. I'm going to take the starting row and the splitter rows, or the splitter lines. Sorry, I meant the other way around. So I get the first line, which has the starting position here, and then every other line goes there. And now what I'll do is, I'll go through the different lines of my file, the successive lines, and I'll create sets that hold the positions of the splitters. So the splitter rows, that's going to be a list of sets. So for line in all of my splitter lines, I'll create a set with the splitter positions, which are given by the indices where the splitters live. So I enumerate each line, and if I find a cell that is a splitter, I keep its index. And this set might be empty because some rows have, or some lines of the input file have no splitters whatsoever. So I only append to the splitter rows if I have any positions, if I have any splitters, otherwise I don't care. And then I'll return the start line. I'll grab the starting position from it, and I'll return the splitter rows. Now if the name is main, I'll grab the starting position and the splitters from my inputs. So now let's grab the input from Advent of Code. Let's save this. Day 7 input.txt. Okay, so the answer should be 1711. Let's see if we can get that. So for part 1, what I was saying is that Excali draw, I'm gonna look at the collection of diagrams we've been drawing these past few days. So I'm going to look at the collection of splitters. So I'm gonna have a bunch of splitters. Actually, let me separate this by row. And for each row, I'm going to have a set of beam positions. And for the next row, I will know the indices of the splitters. And now there's two types of beams. I can split the beams in two groups, or I can divide them in two groups. There are beams that will hit a splitter because they have the same position, and there are beams that will not hit a splitter. So the green ones, I know I have to split the beam. So for beams that will hit the splitter, I split the beam. And for beams that don't, I just let them be. So this is the division that's going to be important, figuring out which beams split and which ones don't. And I can do this easily with sets, because the whole point of using the sets is I don't really care about the empty spaces. I don't even care about the order. I only care about the positions themselves, the numbers that hold the coordinates. So now, part 1, I'm going to take the starting point and the splitters. And now my beams, so this is the set of beams that is going down. And it's a set that contains only the starting point, because in the beginning I have a single beam. Now I'll go through each row of splitters, and I'm going to divide my beams in two types. So there's the beams that hit a splitter, and you can find those by taking your current set of beams and intersecting with the splitters. So let's call this maybe splitter positions, because it's plural, splitter positions. And there's the misses, the beams that don't hit anything, which are the beams minus the splitter positions, right? Or really, you could think that the misses are every single beam that is not a hit, but this simplifies to the splitter positions. But you can leave it like this if you prefer. It's equivalent. So there's hits and there's misses. So for the hits, you have to create new beams. So the new beams are created by splitting the beams that were a hit. So you need to create a beam to the left and a beam to the right. So you can do that with two sets. The beams to the left. So for each hit, you're going to take the beam and subtract one for each beam in hits. And you do the same thing, but you add one to create the beams on the right. So these are your new beams. And for the next iteration, your full set of beams is now composed of whatever misses you had, plus the new beams that were split. And this creates a set for the next iteration. And this goes through the full grid, and when you're done, you know exactly the beams that you have. Now I forgot to keep track of the most important thing, which is the count of splits. So the split count starts off as 0, and we have as many splits as hits. So after computing the hits, we can update the split count. And when we're done, we return the split count. This should be enough for part 1. Let's see. So we're going to print part 1, start and splitters. What do we get if we run this? Let's see. We get nothing because I don't know how to write Python code. Line 9. I didn't mean to... This was not supposed to be an if. I'm just appending. Alright. So there you go, and I get 1711, which is my answer for my input, which is the expected answer for my input. Alright, questions about this. Does this make sense or not really? Alright. Missed the first part, but it seems to make sense. Well, hopefully it does, because part 2 is going to leverage this idea pretty heavily. So you kinda need to be more or less comfortable with this splitting logic. Now, the truth is, using sets here makes sure you only keep track of the positions that really matter, but you could also go through the full grid and note where you have beams. That would also work well. But I think using sets is nice because you get to use all of these set operations that simplify your life. Very well. So on to part 2. If you think of any questions in the meantime, feel free to ask. Let's see part 2. So for part 2, you still care about the grid and the beam splitting, but now instead of counting how many times there is a split, you want to count the total number of paths that will take you to the bottom. Alright, so now you want to figure out in how many different ways you can go to the bottom. And the problem here, or the difficulty with this, is that you can see, for example, the beam that's currently on the screen, where the beam goes left and right. It alternates between going left and right each time it splits. And it ends in a given position. But there are other beams that take different paths and end in the same position. For example, this one goes left a bunch of times and then right, left, right, and then ends in the exact same position. So there's a lot of overlap. There's lots of beams that end in the same position, but that overlap in their path. Hey there, really is it fun? For the example input, we have just a handful of splitters. There's 22 splitters in this diagram, and there's a total of 40 different paths. But for your full input, well, yours is going to look yours is not going to be exactly the same as mine, but the input is much, much larger. As you can see, it's very, very large. And what this means is that you can't simulate all of the paths because the final result is huge. For me, the final result is, I don't know what this number is. This is the thousands, this is the millions, this is the billions. So it's roughly 37 trillion paths. So there's no way I can simulate all of them. So we need to do something clever about it. Now there's a couple of different ways of solving this. But what I'll do is I'll go with a solution that was inspired by my first part. So in part 1, I have a set that keeps track of the positions of the beams. Now what I'll do is I'll still keep track of the positions, but this time I will also keep track of the number of beams that I have there. So what does this mean? Now I need a better diagram. So let me copy the diagram here. All right, let's do screenshot. Let me take a screenshot of this. Okay. And now let's move this to Excalibur. And now zoom. Can I make this larger, please? Yes, I can. Brilliant. So what I'm doing is starting with a single beam. I'm starting with a single beam, so I keep track of its position, but also the count. And whenever I hit a splitter, I need to split the beam, and I will the beams that split will keep the same counter, because this counter is the total number of beams that share this part of the path. And up until this point there was only one beam, so there's only one way of getting to this position, starting from the top. And we keep going down, so we go down this row, nothing happens. And now this is where things get interesting, because I'm going to split here on the left, and I'm going to create a new beam here. Actually, let me do the following. Let me... can I erase? No, okay. So the beam, I split the beam. Let me do this in two different colors. So it's split. The number stays the same, but it's split. In here, nothing happens. And now this is where things get interesting. Let's focus on the left beam first. It's going to hit the splitter. It's going to split into a left-left, and the number stays the same, and into a right beam with the 1. But now, if we look at the beam that's on the right, when it hits the splitter, it's also going to create a beam here with the same number, and to the left of this splitter, you're going to create a new beam with the same number. But now the problem is, you have two beams that came from two different places in the same position, which is not allowed. So what you do is you combine them and you add the numbers. So you do... Oh, this is going to be fun. How do I erase this? Yes. So we have the one here. And now you combine the beams in the center. And you add the numbers. So you get the 1 plus 1, which is, as you know, 2. So when you keep going down, you have the red with 1, the orange with 2, and the blue with 1 as well. And now, when you hit the next region, you're going to have a similar thing. So the red one is going to split. You get a 1 here and something here. Let's fill it in later. And for the rightmost beam, you also get a 1 on the right and something in the center. Let's fill it out in just a second. Because now this position is going to have beams coming from the left and the right, and also for this one. So we need to keep track of the numbers of the incoming beams. This one here is going to be 1 plus 2. And this one here is also 1 plus 2. Or rather, let's say 2 plus 1, because the 2 comes from the left. The 2 and the 1 and the 2. So do you get this idea? Because this is enough. If we do this, going top to bottom, and keeping track of a beam with its counter, you can go through the grid just once and you don't have to simulate multiple beams. So when you end with the 37 trillion, you didn't really need to simulate 37 trillion paths. Because at every single point in time, you only have a handful of beams represented on the grid. So this is the gist of the algorithm that we're going to use. Alright, if something doesn't make sense, let me know. I'll move on to the code. Now, there's a couple of different ways of representing this. Even if you stick to this exact idea, there's different ways of implementing this in code. What I'll do is, I like the essence of a set that allows me to keep track of only the positions that matter. But since I also need to keep track of counts of beams, I will use a counter from the module collections.counter. So let's do that. So for part 2, I need to import a counter from the module collections. And a counter is like a dictionary that by default assigns 0 to every key, and that has a couple of niceties for working with counts. And the reason I like something similar to a dictionary is because dictionary keys can also be used with set operations. So that's going to be very helpful. So the initial idea is similar. Your beams, you're going to keep track of your beams, which is given by this counter. And in the beginning, you have a single beam at the start. So in the starting position, you set a 1, which is equivalent to doing this first arrow. Now you're going to go over the splitter positions. And now you're going to do a similar thing. You want to figure out how many hits there are, or not how many, but what hits there are, because when you hit a splitter, you need to split the ray. So you're going to go through each hit. So for hitting beams.keys and splitter positions, here, beams is no longer a set, it's a counter. But the keys of this counter can be used as a set in this operation. So you're intersecting your current beams with the positions of the splitters, and that will give you access to all of the hits. Maybe it's, for the sake of clarity, it might be a good idea to extract this into an assignment. So for hitting hits, so what do you do? Let me open the diagram again. Whenever you hit a splitter, you're going to create a beam on the left and a beam on the right, and you're going to keep the numbers. But saying that I'm keeping the numbers can actually be misleading, because in some scenarios, like the one over here in the center, I'm not really keeping the number, I'm adding my number to whatever was there. So by default, each position starts with a 0, and then you can add whatever counters you have, which allows you to juxtapose your different beams without overwriting whatever was there before. So what I'll do is, I'll take my next set of beams. So I'm going to create a set of beams or a counter for the next beam, so for a fresh row. And I'll say that in the position hit -1, I have to add whatever I had in the current beam. And I need to do the same thing for the split that happens on the right. So this will take care of the splits. Now, there may have been some misses, so I also need to take care of those. So the misses are given by whatever beams I have minus the hits. So for each miss in misses, the next set of beams will, sorry, this should be a miss, will add whatever I have now. So I'll take, again, miss. So I'll take this miss. This is a beam that did not hit a splitter. So whatever counter it had needs to be moved down. And when I'm done with this iteration, I can set beams to be the next row of beams. And once I'm done with all rows, I can just return the total of all beams. And this is a method, this method total is a method from counters. So because I'm using a counter, I get this method for free. Now let's see if I got this right. This is the code. Let's run this. All right, so 367 8365. Let's scroll down. 367 something something 8365. All right, so the solution seems to be correct. Let's look at this code for a second. I'll take a sip of water while you ask any questions you might have. How cool is this? Isn't this really cool? Look, I'm keeping track of 37 trillion paths, and yet my keys, so my dictionary, my counter has only a handful of keys. Let me check how many. UV run. 85. When I'm done, I have 85 keys in the counter beams, which means there's 85 positions at the bottom that beams can end at. And yet I was able to count 37 trillion paths. And this solution runs essentially instantaneously. You don't see that it doesn't take any time. It just runs really, really fast. This is very efficient. I think this is a pretty cool solution. And there have been problems in Advent of Code problems in the past that involve this idea of like the multiverse and keeping track of lots of simultaneous things, and using counters for this type of situation is very, 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 very common. All right, everyone. So if there's no questions about this solution, what I'm thinking, let me just check the time. On another note, if we know the end positions of beams from part 1, is there a possible recursive approach with caching? Yes, there is. So what you can do, and strictly speaking, you don't even need to know the end positions from part 1, but what you can do is, let me take this and do another one. So starting again, you don't necessarily have to start from the bottom, or rather it really depends on how you implement this, but what you can do is, starting from the bottom, you can say that there is a single way of getting to this position starting from the bottom. So for each cell, there was a single way of getting there, because you just started there. So it's as if you, like, if there's nothing above you, there's one way of getting to each cell. All right, so now you go to the row above. So now you ignore everything that's higher than the second to last row. You just look at the second to last row. What do? You look at each position and you check what's under it. If there's nothing under it, so if it was empty, you just copy the number. But if under a position there is a caret, what you know is that the number of ways to go from the currently highlighted cell to the bottom will be the sum of the different ways of getting to the bottom from the left path and from the right path. So what you do is you add up the numbers. So you get a 2 here. And this is a 1, this is also a 2, this is a 1, a 1, a 1, a 2, etc. Now for the next row, you're going to do a similar thing. All of these stay the same, they don't matter. Then this one is a 2 because there was nothing under it. This one you skip because it's a caret. Oh, right, yeah, this was an empty row, of course. So now you just copy these. This is a 1 and this is a 2. For the sake of the diagram, I can ignore all these. Now for this row, what goes here? The sum of the children. So that's going to be a 4 here. And this is a 2. And this is a 3 because you're adding the 2 and the 1. This is a 1, this is a 3. And this is a 2. And you keep going up. And your result will be whatever number shows up in S. So this could be a different way of doing it. And now you're starting from the bottom and going up. Now, this is just a description. Now, depending on how you implement this, you might end up having recursion with caching. Yes. If you literally start building from the bottom up, then I would call this dynamic programming. If you start from the top and call the functions recursively and have caching, then yeah. But it's probably this idea that you'll want. Alright, no problem, thank you for the question. Now, I'm thinking, again, let me check the time. We have half an hour, because I can only stream for roughly 1 hour. So what I'm thinking is trying to create a a visualization for the second part of today's problem. So I want to create a visualization where we have different splitters and we see the beams going left and right. I think that could be quite cool. So how do we do that? Well, let me check the size of my input. What I'm thinking of having is just represent these splitters as small. So essentially my screen will be a grid, and I'll represent the splitters as I don't know, squares of a fixed color, and then the paths as they go down will have a darker shade of whatever color I pick when there are more overlaps. So as the beams go down, you see the sides getting lighter and lighter, and the center positions getting darker because that's where the higher concentration of beams is. That's what I'm thinking. Let me just see how many positions I have. So character count 141. All right. So I'm just checking the length or the size of the, and how many rows do I have in my input? Let me see. 142. All right, we can work with this. So let's create our visualization. Let's use Pygame. UV add Pygame to this script. All right. Now we're going to load the input. By the way, what I'm thinking, instead of having a real-time visualization, like, actually we might end up having both. But I don't want to focus on the real-time visualization. I want to render the frames and then create an animated GIF out of the frames. So I'll open my input in read mode, and I'll read the whole thing. All right, and now I'll get the grid width is the length of, actually I want the lines. No, I want the split lines because I don't want the line ends. So I'm going to read the whole thing and then split the lines. So this is the input grid. The grid width is the length of any row, and the grid height is the length of the input grid itself. And now let's say that each cell in my screen is going to be a small square of, I don't know, 4 by 4 maybe. So the screen width is the grid width times the cell size, and the height is the grid height times the cell size. So now we can create a Pygame screen with height. And now let's fill the screen in white. Let's create a couple of colors here. So white is this, black is 0, 0, 0. So we fill the screen with white, and now we're going to draw all of the splitters. So for Y row in the enumeration of my input grid, and for each X and cell in my enumeration of my row, if the cell is a splitter, I want to draw the cell at this position in black. And what is the function draw cell? Let's define it here. This takes an X, a Y, and a color, and it's going to draw a rectangle, which is really a square, on the screen with this color in the given position. And now these are X and Y are coordinates on my grid, so I need to convert the grid coordinates to the global coordinates, but that's just multiplying by the cell size. So this is the top left corner of my rectangle, and then we give it the size of the rectangle to create the cell. Now this should be enough to draw my cell, and now we flip the screen to update it. And now we just have a simple loop to manage the Pygame events so that the user can exit the Pygame window. So for event in Pygame, if the event type is the user trying to quit, then we just quit. Now let's run this and see if this is a decent start. Pygame is not defined. What did I do? Did I not import Pygame? Brilliant. So let's import Pygame. Let's run this again. Now Pygame needs a second to start the first time around. Alright, so this is our input grid. Can we make this larger? We can make this slightly larger to make it easier to see. Let's try a cell size of 6, see if this is still reasonable. Alright, so this is our input grid. Now what we're going to do is have a beam go down the tree, and the colors of the beam will be darker where there are more paths. Yes, that's what I'm thinking. Alright, so let's do this. First I want I know someone in the chat asking if I knew React got hacked. I have no idea, and since this is Python, I don't think it's going to be super relevant, but okay. Alright, let's create a folder for the frames, because as we render our visualization at each step, we want to save an image. And oh, Ivan, if you're saying if you want to learn more about Pygame for cool visualizations, well, there's two things. Okay, I'm sorry, I have to say this because I have what is it? The little book of Pygame. So I have a small book, a short book where I teach the basics of Pygame to create four mini games, because Pygame really is for games. But if you want, I'll paste the link in the chat because why not? But if you want like a very cool tool for visualizations, if your purpose really is visualizations, then maybe Pygame, Pygame isn't the best thing ever. It's just the one I use because it's the one I know. So if your goal is visualizations, try to learn, what is it, Manim, I think? Yes, Manim. This might be, well, just check the style. You might prefer this one. I'll paste the link in the chat as well. It's a very cool Python library that a very famous YouTuber started developing for his own visualizations, and now it's a project that the community supports, and it's a really cool library. For animations, you might prefer this one. Okay. So let's go back to, where is it? Let's go back to the code. Here it is. Great. So now what we need to do is, again, simulate the going down, which is essentially what's happening in the part2 function. But whenever we are done with an iteration, we're going to color the respective row. That's it. So actually I'm going to, Yes, I'm going to copy this code because we're going to use this. I'm going to copy the code. I'm going to paste it here. And I'm going to dedent. So what do we need to do here? So this runs the simulation. What's the start? I haven't defined it yet, so I need to look at the input grid, the first row, and find the index of the S. That's my original beam. Okay, now this will go through each row. So for each row, and this should be the input grid. Yes, yeah, 3 blue, 1... I'm sorry I didn't mention 3 blue, 1 brown by name. Yeah, I don't know why I didn't do it. Yeah, 3 blue, 1 brown is the famous math YouTuber that created Manim. Initially as his own... the tool he used for his animations, and eventually, I think, maybe he open sourced it. I don't know exactly how things came to be, but nowadays you can use Manim yourself. Alright, so now there's a slight mismatch between what the simulation code has or assumes and what we have. We can fix this easily. We can just do what is it? The splitter positions. The splitter positions are given by the indices where you have splitters for each row. So you check for splitters, you build the set of splitter positions. The next beams, you compute the hits and the misses. All right, now at this point, over here, before we update, actually I think it's irrelevant, either before or after. At this point, we know for the current row, we know exactly how many beams there are in each position. So what we want to do is go through each position that has beams and color that cell. So we're going to do that. So the total number of beams in this row is given by the total, right? And now we go for each beam, for beam in beams.keys, we have a position, and now we need the percentage. So because we want a darker shade of whatever color in positions with more beams, we need to know what percentage of beams are in this position, so that we can get a nice gradient effect. So the percentage of beams is given by, we can actually do beam count if we go through the items. So the beam position and the beam count, the beam percentage is the beam count at this position over the total beams in this row. Again, it's in this row because the total number of beams increases as you go down. So the beam percentage is this. And now to make it simpler in the beginning, let's just do a very basic gradient. So we'll paint the beams in red, and the maximum red you can have is 255 in RGB, and we just multiply this by the beam percentage and we convert this to an integer. So this will give us a number between 0 and 255. If I have a lot of beams here, it's going to be a strong shade of red, and if I have a small number of beams, I will have a faint shade of red. And now I'll draw the cell at the current position. So the beam position, I need the row index, which I don't have yet, and the color, which is going to be given by this shade of red in RGB. So red, green is 0, blue is 0. Now the row index must come from here. So for row index, row in enumerate of the input grid. And once we're done drawing this row, we flip the display. Now, I don't know if this is correct, so let's run it and see what happens. Name counter is not defined because I forgot to import. Oops, let's try this again. It kind of worked and then it didn't. Is this stuck in a loop or what's going on? Let's see, can I close it? Yes, okay, so we saw something on the screen. It's not what I expected. Where is it? Okay, it's here. Now it stopped even earlier. Now what's interesting here is it's not stuck in an infinite loop or anything, because if I close it, it closes, which means it's hitting this piece of code. So the problem lives here. What's the input grid? Is this not the full thing? Input grid from the input txt, which I did not modify. Alright, if you see the problem, if you see the problem and want to help me out, let me know. Otherwise, if you want to see me suffer, then don't say what's wrong. So we start in the correct position. Like if there's no splitters because some rows are empty, what happens is that beams.keys gives you everything, splitter positions is nothing, so this is empty. We don't split anything, and because hits is empty, we get all keys as misses. So they stay in the same position. And then the drawing should work for beams, the beam count and the total beams. And the draw cell X, Y, color. Let me check that because the output doesn't seem to have all rows. So let's print all rows. UV run vis.py. Wait, so it does go through all rows. It printed all of them, but it's not displaying them. Which is really weird. So we see the prints, it went through all rows, but it doesn't look like it's drawing them correctly. Beam count, total beams. Is this such a small number? Let's print the reds. Because it might be that no, but 000 is black. Wait, black, and I want the... Okay, now let's print this red to see if this is a weird number that's not... Okay, so when you get to the bottom, you are getting zeros, which means your beams should be black, but you don't see black paths. Okay, interesting. Huh. Let's do max 120. So let's make sure I get at least some shade of red in every position. So even when I make sure that I still get some red, I don't see the red going down. Okay, why not? Draw cell. Where's the function? Okay, let's do the following thing. Let me print the row index. Let me print the position I'm about to color. With the color, when I'm done, I'll print a separator. And I only want to do the first 10 rows. Is this going to be enough? Let's do the first 20 rows. Alright, where's my... So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the output is just disappearing. What's going on? Why don't I see these cells? Well, folks, this is not the most exciting thing ever. I have no idea what's going on. No idea. Let me try something else that's stupid, which is to flip the display at the very end. Just to see if something magically shows up. Where's my Pygame window? Oh wait, more stuff is showing up now. Let me do 30 rows. This doesn't seem to be drawing any longer, right? Let's do... Yeah, it's just stopping at some point. Any suggestions from anyone in the chat? Does anyone have any clever ideas? Because I'm not sure what's going on. Okay, I'll do another brilliant thing. I'm using the full input. That's why I'm very confused. I'm reading the... Oops, where is it? I'm reading the full input file, input.txt. It has the whole thing. And yeah, I don't even have the sample here pasted anywhere. I'll do another brilliant thing, which is after each row, I'm going to pause while paused, and then if the event type is key down and the event.key is the space, then we stop the pause. So we run this again. UV run. Alright, so now every time I press space, I break my code. So every time I press space, I should get a new row. No, I don't? Why not? Oh, wait up, come on. If event.type equals paused equals false, my bad. My brain is no longer working. So I press space, I get a new row, space, 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 space. Right, so it's splitting. Yeah, I see the question about rendering not keeping up, and I thought it might be that, but in the end, oh wait. Now I'm just repeatedly pressing space. Of course you can't see my hand, but I'm repeatedly pressing space and it's filling the tree. So was it that you were right? Rendering can't keep up with the computation in some way. Well, that's weird because I was like I even flipped the screen one last time before showing everything. I'm traveling through my manifold, yes. Maybe what I can try doing is I can update just this region of the screen. And this will be more efficient. So I start at 0 for the X, so from left to right, but just a small sliver. Y is the row index times the cell size. And now the width of this small sliver is the whole screen. And the height is just cell size. Will this work? Let me, where is this? Let me remove the comment, the manual pause. All right, this was much better. Okay, so the problem was I was updating the full screen too often. So now we can see the update in real time. We no longer need to print. Now let's get rid of this max to see if the shade of red looks reasonable. It's not going to look great, because right now it's linear, so it's going to look like it's empty on the sides. And also I get the black because I'm doing this wrong. What do I need to do? Actually, what I need to do is convert the red into white. So I want to fade the red onto white. So this is actually 5.5. What's going to change is the components of green and blue, because white is 255, 255, 255. And the smaller the beam percentage is, the closer to 255 we should be. So red is always 255. Green and blue are equal to 255 times 1 minus the beam percentage. So now let's see if we get shades of red. Yes, closer, but also very wrong. Right, this should be green and blue, my bad. Now there was a print that's annoying me. This can go away. Let's run this again. Okay, so this is much better. Awesome. Now, I don't know if it goes through in the stream, but we have a very strong shade of red at the top. And more or less around the center, you can see a faint pink. Kinda. What's the problem? The problem is that there are so many paths that the percentage of beams, even though it's much more concentrated in the center, it's still a very small percentage. So what you need to do is you need to convert you need to, what's it called, rescale the percentage using something, it's up to you what, to make it so that even these small percentages are much more noticeable than the tiny percentages on the edges. So what we can do is, let's see how much time do I have. Aha, no time at all. Okay, we can spend 2 more times. We can spend 2 more minutes doing this. Also, Ivan suggests swapping the white and the black for the background and foreground. That might help. Let's see. Let's set the foreground. So you say the background black and the splitters white. So I'm filling my backgrounds, and then you're saying that the splitters should be white, and that will make the red slightly more visible. Okay, let me close this and run this. Whoops, I did this because because now I need to fix the computation of the color. Wait, I did this wrong again, because why? When this is small, Oh no, right, now it's... Sorry. Can I close this and run it again? Yeah, it doesn't help a lot. Now I think this will be worse for you. I can see a very faint red in the same region, but this is worse, I think. But the solution really is... I mean, of course I can pick background and foreground colors that are slightly better, but the major fix is the rescaling. So what I'll do is, instead of having a linear scale, let's see, what's that called? Sigmoid. I think this helps. Or actually maybe just a logarithm. The logarithm might help, but then it's just a matter of tampering a bit with the numbers. So let's try a logarithm to change the colors, and then we will call it a day. So I need from math import the logarithm function, and now what I'll do is, give me a second. My dog is complaining about something, which is probably just the neighbor existing. So what I'll do is, instead of using this division here directly, I'll compute the log of everything, or I'll do the division over the logs, which should make it so that total beams log, so that even the small numbers are slightly larger. I mean, this was a very poor explanation of what I'm doing, but we'll see if it looks better. Total beams log, yes, I meant total beams log. Division by 0. Why? Oh, because it's 1 in the beginning. Beam percentage. If total beams log, else 1. Alright, much better. Not perfect, far from perfect, but definitely much better. Now you would need to tweak this a bit so that even the paths on the edges are slightly visible, and to create a greater distinction in the center regions. But yeah, definitely better. I hope you folks agree that this is better already. And I broke something. At the top you don't see the paths. Alright folks, I think we will call it a day. I have a private session I need to go to now. So let me commit this to... No, I have to fix this. What's going on here at the top? This goes 50-50. Why can't I see anything? Oh, because this will be 0. Because the beam count is 1, so the log is 0. You know what's a terrible way to fix this? This is super hacky. I have a maths degree, so I shouldn't be doing this. But I can do this. And now, if I run the thing... Alright. Much better. As in, the top is now clearly visible, and even the edges have a tiny, the faintest shade of red. It might not come through in your screen, but I can kind of see it. Again, this would need more tweaking and fiddling. Alright, enough of this. Let me push this, git status, git add day 7 visualization. Oh, and I forgot to save the frames to make the GIF, but we'll leave that for maybe tomorrow, we'll see. So this has now been pushed. I'll paste the link in the chat in case anyone is interested in taking a look or playing around with this. There's also, if you go to Reddit, there's other folks doing other visualizations. Some are better, some are worse, some are similar, some are different. But still very cool stuff. Thank you everyone for watching. I appreciate you being here, and I'll be here tomorrow at 5 PM UTC to solve day 8. Bye everyone.